In this video for Lab 2, I will discuss the motion of a falling object, which in our case is bread, and analyze this motion using 3 different methods. The first method is by utilizing the tracker software and extracting position versus time data. The 2 other ways involve Python. Here, I will predict its motion using only the effect of gravity, and then predict its motion by using the effects of gravity and drag. In this lab, I will explain why the graphs with gravity and drag are practically the same. In addition, I will note why drag force does not make an impact on the bread's position. This result is non-intuitive for some at first. Finally, in this experiment, I concluded that drag force, which is a resistance force caused by the object moving through the air, was always opposite in direction to that of gravity. Now let's take a look at the tracker software. Let's watch as the bread falls from rest. As you can note, these dots are as the time is an equal time interval. As you can note, the dots are closer then get farther apart. This means that the velocity increased. Now let's look at this graph of motion. As you can note, the slope is less steep and then gets steeper. Since the derivative of position is velocity, you can note that the velocity does increase with time. Now let's discuss and analyze Newton's second law and the momentum principle. In our case, the final velocity was greater than the initial velocity. This means that the net force couldn't have been 0. The equations to find net force are shown below. As you can see, the drag force, which is this equation, was very small due to the fact that the B constant was 0.01, and because the object did not fall a great enough distance to produce a high velocity. Therefore, the net force was relatively constant. However, the acceleration was still present, which made the object gain speed and momentum. Once again, we know the object gained momentum because the velocity increased over time. So in other words, the weight force basically dictated the net force. So once again, let's look at this graph that we obtained via tracker. So the slope gets steeper, which means the velocity increases. Although the F net was constant, the final velocity after each time interval transformed into the initial velocity for the next. That is why the final velocity kept getting bigger and bigger and the slope got steeper and steeper. Now let's look at how we constructed both models. So in both models, you needed the mass in kilograms because that's the SI unit. This was the mass of the loaf of bread. And the initial position was obtained via tracker software, so it was a little not on center, but it was basically at the origin, and the velocity was 0 because it was at rest. I changed the time step to 0.01 in order to better correspond with the tracker data. In addition, the gravity was set to 9.8, which is constant, and this vector just says that the y-axis points up. So now let's get to the part where the two differ. In both cases, we use the time less than 0.402, which is how long it took the bread to fall. With the gravity and drag, you had the weight force and the drag force equation, and that produced F net. However, in this model, you only had the weight force equals F net. Once again, both had Newton's second law in it, and the updated position. However, as you can note later on, the 2 models are practically the same. This is because the drag force is really small. The B constant was 0.01, which was very tiny, and the magnitude squared of the velocity also produced a very tiny number. So as you can note, the data does not predict the model. The 2 lines using data from the computer have a perfect parabola shape, while the observed motion doesn't. This is due to the fact that it was hard to pinpoint the center of mass with the blurs. However, aside from experimental errors, the graphs are different because of the small time interval. Because the fall was short, the drag force was very small. Finally, the B constant was very small, 0.01, which greatly decreased the drag force. In conclusion, with more distance covered, the graphs would be separate, with the model using only gravity falling more distance due to the fact that drag force slows down an object. Or in other words, the object would fall the same distance in less time. So now we have to see if any models predict a terminal velocity. Terminal velocity is reached when the drag force equals the gravity force. Therefore, there is no acceleration and the velocity is constant. From the graphs, it appears the terminal velocity was reached on the model with gravity and drag. The slope stays relatively constant, just like in this example. There is no change in slope. However, for the terminal velocity to be reached, the object would have to fall a greater distance. So if an object was thrown downward, the terminal velocity would be the same. However, the time it takes for the object to reach terminal velocity would be different because the object thrown downward would have to decelerate a lot more in order to reach zero acceleration. So in both cases, it would end up like this, but one would just take longer. So in conclusion, as the bread dropped, it gained speed and momentum. Therefore, there was a net force acting on it. In addition, the computer models that predicted the motion of the bread falling should be different with the model excluding drag falling further. However, in our experiment, the weight force surpassed the drag force due to the mass of the object being much more than that of a simple piece of paper.